Thank you very much. First of all, every Friday up to now I forgot to do something, but today I did not forget, and so here is the prize to demand for asking the best questions in the class. Good. As usual, I have run out of time, and so I cannot say everything that I wanted to say. Instead, I will, to a certain extent, I will repeat myself, say again some of the things I already said. I want to make sure we learn at least something, even if we don't learn everything. So the subject of today will be not exactly as advertised. It will be more about these famous discrete series, and then we shall return to the C-star algebra, try to make a conclusion. But we will not get quite as far as I hoped we would. This is life. Okay. So we were discussing, and we'll discuss it again, this strange, maybe strange statement of Connes and Kasparov. It involves some strange thing, K-theory, and so on. It's related in an obvious way to the discrete series representations of one of these reductive groups, and in a less obvious way, it's related to the entire tempered dual. And so we'll try to connect all of these ideas together. I should say that the subject to me is still a mystery. The final way in which these three things interact, to me, is not completely understood. So there's still some work to do. The connection between these two, I think, is becoming very clear, thanks to the work of many people. Some a long time ago, starting with Partha-Sarathy and Atiyah and Schmidt back in the 1970s. But when you try to put everything together, then it becomes a little mysterious how best to think about all of these things together. Okay. And, okay, so let's remember what happened last time. We defined a certain map, a homomorphism. So let me just emphasize what these things are. These are just countably generated abelian groups that we're talking about. In fact, they turn out to be free abelian groups on a countable number of generators. And over here is essentially the representation ring of K. In fact, I'll make some assumptions, and that's exactly what it is. So another way of saying this is that it's just the free abelian group on K hat. And I want to say that the following thing, that thanks to the work of Hermann Weyl and others, this is completely understood and very simple. Well, simple from a certain point of view, at any rate. The full description of this in general involves some Weyl group. It involves some theory of permutations. So, in fact, if you want to put it on a computer, it's not so easy, because the permutation, there are many permutations, n factorial permutations. Anyway, this is simple and beautiful, I'd like to say. This is somehow the point. And over here on the other side is something which is a little bit mysterious. It is this K theory, K0 if you're keeping count. I apologize for these two Ks. These Ks are completely different. Sorry. Of the C-star algebra of G. And what exactly goes into this is a little bit hard to say. So it's made, as we saw, the definition is it's made out of homotopy classes of Fredholm operators, some crazy definition, but let's just say it's homotopy theoretic in character. But, of course, it also involves the group G, but involving G, and in particular the tempered dual of G. And these two things are mysteriously related. This object is very, very complicated. And when you do this to it, you make the C-star algebra of G as some sort of object which is stands in for this topological space, and then you take the K theory, then you get something which miraculously turns out to be rather simple, because it's equal to this. And there's this map here given by index of Dirac. And, okay, so this is the character of this. Something very mysterious on the right-hand side has a very simple description on the left-hand side. You wouldn't necessarily expect that anything about this space could be described in a simple way. If you read the books, if you read the textbooks, you will discover all of the details of tempered representation theory, and they look very complicated. And it's a sort of miracle that such a complicated subject as the theory of this tempered dual fits into something which is rather, rather simple. Okay, in a non-trivial way, as we'll see. Anyway, there are some assumptions which go into this statement, so let's just make sure we understand those. So G should be one of our real reductive groups, at least the way we've been discussing it. Okay, it's the maximum compact subgroup. And if you want this to be correct, in the way it's stated, we should let G be connected. And compact center, well, that follows from the next thing I'm going to say, which is that T is a maximal torus. Okay. There's a funny condition, which is that the centralizer in G of T should be compact. This is exactly the condition you need so as to guarantee that this group has discrete series or compact representations. So as the representation theorists would say, discrete series representations, as we define them in this class, compact representations. But there's another aspect of this isomorphism up here which is very, very interesting. Even though I made some assumptions, I didn't have to. It just allowed me to slightly simplify this statement. It's not that much more difficult to throw away, boom, 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 throw away all of these assumptions, all of these three assumptions. In fact, even this one. there's almost the same sort of statement, almost as simple, just a little bit more complicated. Like this one up here. Without any of these assumptions. In fact, although we've been talking about these reductive groups in these lectures, the group G can be any Lie group. When I say Lie group, I don't want to allow arbitrary discrete groups. That would be a little too much. So let's say almost connected with finitely many components. And I didn't put it in here, but it's, maybe I should emphasize this. It's a true statement. It's a theorem. So there's some beautiful truth about all Lie groups, and in particular about all real reductive groups along these lines. And it's very hard to find in representation theory anything like this. If you start to relax these assumptions, particularly the first one, then all of a sudden it's very hard to classify anything. Nobody really has written down a list of all of the representations to completely describe this space in the situation where you throw away connectedness. I mean, you could do it, but it would be very complicated. But here this statement is sort of universal. So it's a very strange and beautiful thing. It's just the truth. And it's a relatively simple truth. I won't discuss it, but there's a conjectural statement in which you can throw away the almost connectedness. In fact, you can throw away the Lie group part. There's a conjectural statement which makes sense whenever you can form the C-star algebra. In other words, whenever G is a locally compact group, there's a conjecture for what this thing is. A conjecture for what to put here. That's the Baum-Kahn conjecture. And that's maybe makes it even more remarkable that there could be such a broad truth. Okay. And it's a strange statement, as I say, because over here we're in the world of, I don't know, cohomology, homotopy theory. Over there we're in the world of representations of compact groups, and the whole thing is saying something about representations of non-compact groups. So a lot of different things are mixed up together. Okay. And what else should I like to say about this? Let's examine this in an example or two. We're making all of these assumptions to make our life a little easier. Since we are going to make all of these assumptions. Then this group does have these discrete series. And each time you have one of these things, you get a class over here. If this is one of these discrete series representations. There's a class pi, which lies in this group. And these are all distinct from one another. In fact, they're all linearly independent from one another. And so in a certain sense, you can see the discrete series inside of the right-hand side. So one can hope to understand the discrete series in terms of this map here. So we can hope to relate this star to the problem of classifying, the problem solved by Harishchandra, the problem of classifying or the classification. Discrete series. And this is exactly what happens, as I was trying to say last time. And so let me say a few more words about discrete series. I'll draw some pictures to relate it to this picture in more detail. And then we'll look at the C-star algebra of G in more detail, the temp and dual in more detail. But let's one. Let me see. Maybe I'll start by just summarizing what Harishchandra said. And, oh, hang on, there's a small, just to be honest, I want to add a small point here. I should have. Small technical point. My apologies. There's a small spin orientation hypothesis. Like all of the others, it's not strictly speaking necessary, but if you don't have it, then you have to change this side a little bit. So let me just remind you what goes on. If you take this, if you take the Lie algebra of K, according to the way in which Clifford algebra theory interacts with Lie theory, which is a beautiful subject in itself, there's a map from K, a Lie algebra map actually from K into the Clifford algebra of P, the degree 2 part of the Clifford algebra of P. And there's a map from this into the unitary operators on S, where S is the so-called spin representation of the Clifford algebra, so the Clifford algebra of P. We know this is a matrix algebra, and let's just explicitly write it as matrices over S like this. And what we assume, I almost ran out of space, is that this Lie algebra map lifts to K. Squeeze it in here. We assume that map, this is a Lie algebra homomorphism, lifts to K. So it's a technical thing, but let's be honest and remember the technical things. If you forget the technical things, then surprising consequences can ensue. You start to draw pictures, you try to do some bookkeeping, you try to understand this isomorphism, and if you forget this little fact, you can see, something strange and paradoxical and contradictory happens. So if you forget this, to add this last point, then you will be reminded later on when you do calculations and you see something is wrong. So there it is. You can, in other words, you can notice this by just drawing pictures. All right, so back to Harishchandra. Sorry about that. Here's what Harishchandra said. It's a little funny how this goes. We'll do it down here. And it relies on a funny thing. Of course, the groups we're considering are groups of matrices. We assume that they can be embedded in GLNR in some ways. They should be closed under the transpose operation. It's the main thing. Oh, and closed in the topology of GLNR. That's it. together with these assumptions here. And it's very useful to build a group related to G, the compact form. So here we are inside of GLNC. And what we want is that the Lie algebra of U should be the K plus the square root of minus 1. So we're writing the Lie algebra of G as K plus B. The matrices in the Lie algebra we decompose into skew-symmetric matrices and symmetric matrices, which we're allowed to do because G is closed under the transpose operation. And then you make this funny construction here. When you do this, every matrix in this collection is skew adjoint. The conjugate transpose is minus the matrix you started with, so you get the Lie algebra of a compact group. And because the Lie algebra doesn't completely characterize subgroups, let's also say that K should sit inside of U, and K should meet every component. Oh, I don't have to say that. Sorry, because I'm assuming G is connected, so good. But in general, this group has the additional property when it's disconnected, when G is disconnected, that the number of components of U should equal the number of components of G, which is equal to the number of components of K. Okay, so this is the first funny thing that you need in order to understand what Harishchandra had to say. And what you're supposed to do is, let's do it this way, actually. Let me think about this. Two possible ways of describing. Oh, okay, fine. Let's do this one. Change my mind. Harishchandra's classification. Using Dirac operators. That's useful because this map is defined in terms of Dirac operators as well. Oh, one more thing about this construction is that if T is a maximal torus, okay, and T is also maximal torus of U. This here is a consequence of this funny statement here. Think about it. It's not quite, it's not difficult at all. Okay, so how does this classification go, and what does it have to do with this thing? Let's consider this group here just for an example, in which case K looks like U2. So these are 3x3 complex matrices which preserve the quadratic form given by the matrix 1, 1, minus 1. Inside of that, there is the subgroup, which is a block upper 2x2 matrix group consisting of, well, U2s in the block, upper 2x2 block, and then the inverse of the determinant of the matrix in the upper. Maybe like this. this U group is just SU3. Okay, so T is quite easy to describe. Here's a good maximal torus sitting inside inside of all of these groups. Okay. And now I'm going to draw a picture of all of the irreducible representations of T. So an irreducible representation of T is one-dimensional, because T is an abelian group, and it's given by two integers. And but because of the strange symmetries of the situation, rather than drawing these pairs of integers in a rectangular array, it's better to use such a picture as this. And let me see how it is that I want to do this. So let's represent characters of T by pairs of integers, n and m and n. And so let this be, for example, the n-axis, and this the m-axis, and then this would be the line n equals m, like that. Okay. And then characters fit into an array like this, and so on. And this is a picture of T hat. And there is the marvelous theory of Hermann Weyl, which tells you how to draw a picture of either K hat or of U hat using T hat. And so let's do that next. I'm going to draw a slightly different picture. Same lines, and I hope I'm doing this right. I actually worked this out before I came. Yep, okay, good. What I'm going to do is something dictated by the combinatorics of permutations, and what it has to do with, where is this magic guy here? Yeah, the magic guy in the picture is this one here. And then there'll be an opposite one here. So when you analyze exactly what Harishchandra said about trigonometric polynomials which are invariant under permutations and so on, when you analyze that exactly, what you see is that two particular characters are relevant. One is minus the other, and that's just it. These are the roots of U2 drawn in this picture. And what's especially relevant is to take this fellow and take half of it. What's a good, try and draw a box. And this is what is called the half sum positive roots. It's no longer a one-dimensional irreducible representation of G, because you divide it by a half, so this is supposed to be half the way along this line here. And in order to find a place for this to live, you should embed this discrete set into this vector space, the homomorphisms from the Lie algebra of T into the Lie algebra of T like that, by taking the infinitesimal. This is a vector space, and now you can divide by 2, and that's where this dot lives. Okay? And so what Weyl said is that if you inspect matters carefully, then the representations, let's say, of K are obtained by such a picture as this. What I'm going to do is I'm going to take this lattice and I'm going to shift it by exactly this amount. And if I do that, then of course 0 will go to this boxed point. And let's just see if we can understand what will happen? Something like this will happen. This is the lattice T hat shifted. By this element, it's always called rho. And there you go. So it's kind of interesting. What did I do wrong here? Oh, I see what I did wrong. Equals 0 and equals, sure I believe this. Did I do this right? Half. Yeah, I did.
Positive direction is to the...
Yeah, I'm trying to, I really want, I want this line, I guess. So n equals, no, the R group is this line here, so I guess it's okay. I guess it's okay. Okay, so according to Weil, these parameterize. Okay. So this is, see if maybe I drew the picture not so well. That's probably the, let's see, so this is, go half direction. I think this should be 1/2 minus 1/2. How does that look to you guys? Be more like, this is 1, 0, and this is 0, 1. So I want to go half here, put that down here. Okay, maybe it's about right. Okay. What's confusing me? So this, I guess, goes down to there. Okay, good, good, good. So, bad. What I was hoping to see is some squares on one of these lines and not on the other. And something in my artistry has screwed this up because if you take n plus 1, and you add rho to it, you get n plus 1/2, n plus 1/2. Okay, but that's this line. All right. Okay, fine. It is what it is. I think I have it right. It's not illustrating what I wanted it to illustrate, but there you go. This seems to be Yes. Okay, so I'm trying to describe what Harish-Chandra said. And what Harish-Chandra said is that there's a relationship between discrete series representations of G and representations of K, and also representations of U. They're all tied together. And so after obsessing about this picture, I Okay, I think I did it correctly, but I want to draw a second picture. So this is the representations. Okay, as for you. The representations are also given by elements of t hat, or possibly shifted, as we've seen. But now what you're supposed to do is pick only one of these chambers like this. And you have to do some shift. The reason that you're picking one chamber here is you're dividing t hat by the Weyl group of u, which has 6 elements, and the Weyl group of k has 2 elements. So you're taking 50% of t hat upstairs and 1/6, whatever that is, 16.66% downstairs. And there is a shifting here, too, exactly in the same way, using the row of u, and the row of u is equal to something that I know off the top of my head, which is equal to not 1/2, but it's equal to this here, 1/1. And so what you get is this picture here. The row for u is integral. And the representations, having drawn all of these dots, these, I forgot to say what these here, these are, it should be exactly the points in the interior. Again, the interior points. Trust you had. Oof. And what Harish Chandra said is something a little confusing, because it's a hybrid of these 2 pictures. What you're supposed to do is you're supposed to look at classify these discrete series. You're supposed to consider a hybrid picture. In which consider the region for k, but then you consider the parameters which classify the representations of u. That is to say, all of the dots like this. There'll be one down here and so on. So these are the points on the generally shifted lattice. Came about here, which are not on any hybrid way. So it's some elaborate story like this. Now, what are you supposed to do with all of this data? What these points correspond to, or what you can do with this combinatorial information, is build for each of them a Dirac operator on L2 of G mod K. So we were to write this down using tensor product type notation, it would be like this. And what Harishchandra said is didn't say it himself, but it's equivalent to what I'm about to say, is that the kernel in the particular case of a non-singular sigma, which means not on any of these lines. It's the condition of non-singularity. Is a discrete series. Non-zero, and it's a discrete series representation. And you get all of them this way, and you don't get any repetitions, and that's the theorem. All right. But there are singular guys here, like this one, like this one, and so on. There's one down here somewhere. And this is one here. I tell from my picture where it's supposed to be, maybe not there. Yeah, I feel bad about this example because this is unfortunately an example in which, I should write this down somewhere, in which that spin orientation condition is not quite satisfied. So I gave you this example, but it has a shortcoming having to do with what should be on the left-hand side. So in this case, left-hand side of the Connes-Kasparov map is not R of K, which would be the free abelian group on, where is it? Here, on the dots here, the non-singular, they're not dots, squares, the non-singular squares here. It's rather the free abelian group on these dots here, and they don't quite match up. Spin orientation condition fails. But rather the free abelian group on these set of Harishchandra parameters singular or not. So in other words, any one of the circles in this picture which lie on the interior of this half line, whether or not they lie on one of these interior edges. That's what I was trying to say. Oof. Try and see if we can draw this picture one more time. So, okay, happy now. Oops, keep going here. So that is, each of those circles represents a generator for the left-hand side. It's basically the representation ring of K, but not exactly, because there's a funny little shift here. And the shift is kind of important. This is one of the points I wanted to make, because here you don't see any parameters on, any singular parameters here. There are no parameters, no boxes on the lines, but here there are circles on the line. So there are singular and non-singular parameters. Have I managed to confuse you completely? Does anyone understand what I'm talking about still, after this debacle? In fact, I think I told the truth throughout this discussion, but I had forgotten what the truth was, and so the message I was trying to tell you got a little confused.
When you said you shift the lattice for U.
Yeah, in the particular case of U, when you do the shifting, what happens is that the lattice sort of maps right onto itself again. In the particular case of U, if you build a row, a half sum of the positive roots, this analogous object decreed by combinatorics to be the appropriate shifting, then what happens is that the original lattice, here it is, maps exactly onto itself. And then what you're supposed to study, therefore, for the representation theory of U, is exactly the set of lattice points in a single chamber, like in this picture here, these ones. So according to Weil, the dots I'm shading correspond to representations of U. Okay. And it's kind of interesting what happens, therefore. Let's look at this picture here. Let's take, for example, this fellow. And yeah, so this dot represents a discrete series. It is a non-singular Harish-Chandra parameter. So according to Harish-Chandra, there's a discrete series which you can attach to this red dot. How do you attach a discrete series to this red dot? Well, what you do is you interpret the parameter as the information necessary to build a Dirac operator, and then you take the kernel of that Dirac operator, and that turns out to be the discrete series representation. But this dot can also be interpreted as an irreducible representation of U. But so can this dot here and this dot here. So if you look at these three, what I've done is I've taken this red dot and I've just looked at its orbit under the action of the reflection group, which is reflection around these three lines. Of course, it also goes to points here and here and here, but I'm only interested in those, which are Harish-Chandra parameters. So these correspond to three discrete series, distinct discrete series according to Harish-Chandra. One irreducible representation. And that's generally the case. By studying parameters, what you find is that each irreducible representation of U corresponds to a multiplet of discrete series representations, and the number of them that there are exactly the order of the Weil group of U divided by the order of the Weil group of K. In this particular case, 6 divided by 2 is equal to 3. So there's this mysterious way in which U is entering into the picture. And I tried to explain last time why it is that U might enter in a more natural way into the picture. Great. Let's see what else I want to say. I had a second picture here for SO41, but I think one picture is enough. I think we've had enough of my pictures. Okay. There's a discrete series, a Dirac operator. every Harish-Chandra parameter whether or not it's non-singular, so non-singular not. These Harish-Chandra parameters are essentially the same thing as irreducible, as we see up here and as we saw in the other picture, as irreducible representations of K. Not exactly. What they correspond to are irreducible representations of some double cover of K. And the reason that that double cover enters is that the spin representation is also not necessarily a representation of K. It's a representation of some double cover. And the funny combinatorics of the half sums of positive roots guarantee that when you tensor these two representations together, they become, again, not just a representation of the double cover, but a representation of K itself. Because S is not necessarily a representation of K, you need to tensor it with something which is not necessarily a representation of K, only a projective representation of K, so that the tensor product is a genuine representation of K. That's where this funny and annoying shift comes from that I managed to screw up by choosing a bad example. And maybe a good example, because it shows you the difficulty. So you can do this all the time for any one of these representations of K, which is actually a representation of some double cover of K. And there's basically, in this example we're discussing, there's basically a half plane of them. All right. But if sigma is singular, there's no kernel anymore. And in particular, no discrete series. And so the question is, should you just give up or not? So you can ask, does D have some, I don't know, value or meaning in representation theory nonetheless, despite this problem? And that's the question that the Connes-Kasparov conjecture, isomorphism, addresses. So the answer is yes. And that's so we have a nice, fairly regular picture over there. I'm going to choose another beautiful color. The picture, apart from, what we're looking at here is basically a graphical representation of the irreducible representations of K. Not exactly, because there's an annoying shift. But basically, we're talking about the irreducible representations of K. And they all correspond to discrete series, except for the ones which don't, which are these ones. These are the singular guys. And the question is, can we complete the story somehow so that these singular guys also have an interesting role to play? And the answer is yes, and that's what I'm going to discuss next. And in order to do that, maybe it's time to go back and think again about the full tempered dual. We got a little distracted. It means I got a little distracted, and I talked for too long, too many lectures about discrete series. But now we're finished with discrete series. Let's look at the rest of the story for a moment. So in discussing representations, there were the discrete series, and then there was the dichotomy, which said that either a representation was a discrete series representation or it was obtained by parabolic induction. And then we refined that further. And so what's going to happen is that these dots here somehow correspond to parabolic induction. And using some geometry on the group G, comparing G mod K to G mod N, as we discussed, we saw that every tempered irreducible representation of G is a summand of a representation which is parabolically induced. From a discrete series. And the only proviso there is that we have to talk about discrete series modulo the center in the case of Levy subgroups which don't have compact center. And so we can do the following thing. Let's pick a parabolic subgroup of G. I'll block up a triangular subgroup. One of the things we discussed is that when you look at L, you can break up L further into two pieces. So one piece is traditionally called M, and the other piece, I'm going to do it, is traditionally called A. That's unfortunate because there's another group which is traditionally called A in representation theory, and it's different. So what's going on here is that, as we discussed, this is the positive definite part, positive definite matrices in the center of A. Sorry, the center of L. And this is the subgroup of L which is generated by the compact subgroups, all the possible compact subgroups. And it happens that there's always such a decomposition, so you can, of course, put these two things together, and now P is M times A times N. Now, this parabolic subgroup L, and in particular this part of it M, now this is a group with compact center, and it may or may not be connected, but certainly at worst it's a group with finitely many components. And it may or may not have discrete series representations itself, or to be a little more precise in my language, the connected component of its identity element may or may not have discrete series representations. If it doesn't, then in fact we're not going to pay any attention to this particular Levy subgroup. Let's suppose it does. And let's just pick some, what should we call it, sigma, the discrete series representation. If M is not connected, what I mean is that when you, this should be a representation with the property that when you restrict to the connected component of the identity, it is a direct sum. It should be irreducible, but when you restrict to the connected component, it may not be irreducible, but at worst it should be a direct sum of a finite number of discrete series representations. Okay. And now let me reach into your memory and extract from it some of this Hilbert module language, because it's very convenient here. Here's what I want to do. I want to look at A. A is an abelian group, and it has a dual, Pontryagin dual, which is, I mean, it's still an abelian group, but I just want to think of it as a topological space. It looks like a vector space. And I want to build over it the bundle of Hilbert spaces. And let me tell you what the fibers of this bundle are. If I pick a unitary character phi, the Hilbert space, I want to use all of the information at hand, sigma, and phi, and m, and a, and n, which is p, and so on, and do the following thing. I want to induce from p up to g the following representation, sigma, as it acts on M, tensor phi, which is a representation of A. So I didn't give this whole thing a name. What would be a good name? Induction would be good to stick in there. How about just end of sigma? So end of sigma means this Hilbert module of all sections, blah, 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 blah. Sections vanishing to infinity. Now, on each one of these Hilbert spaces, of course, there is a representation of G. It was built as a representation of G. So this C-star algebra acts as operators, in fact, compact operators, on each one of these Hilbert spaces. So the whole C-star algebra acts, as it happens, as compact operators on this Hilbert module. So what we're discussing here are compact operators on the, I guess I was calling them C-star modules. Over C0. All of these Hilbert spaces, by the way, are the same. They're just, as Hilbert spaces, if you forget the representation of G, it's always just the same Hilbert space, actually in a canonical way. This is actually a trivial bundle of Hilbert spaces. And this C-star algebra is not a complicated C-star algebra. That's kind of an important point. If you're not interested temporarily in G and you just want to know what is this C-star algebra, it's a very easy thing. It's just functions vanishing at infinity on this topological space, which is just a vector space, it looks like Rn, with values in the compact operators on a Hilbert space. So over here is something a little mysterious that we want to get to know. Over here is something totally elementary, which is very, very easy to understand. And we have this map from one to the other. So our basic principle, which is this principle here, let's give this a name. Let's call this triangle or something. This is the principle that we proved using geometry of G, and we compared G mod K to G mod N. This principle, reinterpreted in this language, says that the map you get by adding all of these together over all possible p's and sigmas is injective. If there was something in the kernel of this map, it would, well, the kernel would be an ideal, and it would be an ideal. What would this ideal be? Well, according to the basic theory of C-star algebras, this ideal corresponds to a certain set of representations. And those representations, if you think about, so an ideal determines, depending on how you look at it, either an open set or a closed set, either the closed set of representations on which everything in the ideal acts as zero, or the complementary open set. And if you look at the complementary open set, this would be a collection of representations of G which did not occur in any of these representations. But there are no representations which do not occur in any of these representations. So we're done. This map is injective. In fact, let's just discuss the indexing set here. It suffices to consider we discussed this concept a long time ago, standard parabolics, meaning, in effect, parabolics which are literally block up a triangular subgroups. So the indexing set, as far as P is concerned, is just a finite index set. Sigma, on the other hand, is typically an infinite index set. We drew some pictures of the discrete series, and we saw that for a given M, the collection of sigma of course, it may be empty. But the worst it can be is just some discrete countable set in general. And I'm slipping by you here a small detail. I should now own up to. As we've seen before, we're using what's called the C-star algebraists call the C0 direct sum here, which it means that an element of this C-star algebra is just a list of individual elements from each of these terms, and the norms of the elements in the list should converge to zero as the parameter goes to infinity. In other words, for every epsilon, the norms of the individual elements in the list should, almost all of them, all except finitely many of them, be less than epsilon. And it's not obvious that if you start here and you map over here to get a bunch of elements here, depending on P and depending on sigma, it's not obvious that the norms will go to zero as sigma goes off to infinity. P you don't have to worry about. There are only finitely many P's, but what about sigma? So there's a theorem which is being hidden here. Which is a theorem I'm trying to understand better, but let's call it uniform admissibility. And what it says is that the reduced C-star algebra acts on the orthogonal sum of all distinct discrete series representations. Well, we're applying this in the particular case of the group M, but I'll state it here for G. Through the C-star algebra, C0 direct sum as before. So is this a true fact? Well, it is a true fact, and the reason it's a true fact is, well, one of the reasons it's a true fact is you can just calculate based on what Harish-Chandra told us the discrete series are. And so this follows from Harish-Chandra's theorem, the classification that we were discussing. In fact, it follows from something we used on the way to understanding the classification, which was this trace formula we discussed last time. So if you know the trace formula, then indeed, which is part of Harish-Chandra's work, then you know this fact. So I'm not going to say more about that, but that's, just to be honest, there's a detail there. My feeling about this uniform admissibility principle is that it too should be a consequence of the sort of geometry that we were discussing earlier in the lectures, the geometry in which we compared G mod n to G mod k. It should be the case that this uniform admissibility follows from a more refined analysis of the comparison of those geometric spaces, but I don't know how to do that, so that's an open question. If you're a C-star algebraist, then you can make this consequence of something which looks like it's the sort of thing you could attack. Namely this, if you look at the infimum of the formal degrees of all possible pi's, if you knew that this was bounded below, then you'd be in business. In fact, all of these formal degrees are integers, 1, 2, 3, 4, 5, so they certainly are bounded below. But that's a consequence of the index theory work we were discussing. But of course, you'd like to be able to show this a priori, so there's an open problem. So we're trying to understand the tempered dual. I announced that that was our goal, I guess, in the first lecture. In fact, our goal was to understand this C-star algebra. So now let me begin to tell you what this C-star algebra looks like. What we know so far, thanks to geometry and this uniform admissibility, is that this C-star algebra can be seen inside of this gigantic direct sum. Okay? And now we'd like to improve on that a little bit. Oh, by the way, inside of this gigantic direct sum is a collection of summands which correspond to the situation where P, the parabolic subgroup, is all of G. That's allowed. All of G is allowed. And in that particular situation, if G is compact center, this is just a single Hilbert space. And what you see here are exactly the Hilbert spaces here, up here. So that is a consequence of this, but indeed also that contains this as a special case. All right. And okay, back to this thing here. To proceed further, we need to understand to what extent these different summands that appear here are related to one another. So each of these summands comes from a certain Hilbert module, which is made out of a collection of representations. And so what's at stake here is to understand something about this collection of representations. Are these all disjoint from one another, or are these representations all distinct? Are they not all distinct? That becomes important to go a little bit further. And there are some beautiful statements here, which So these are the things I don't have time, alas, to talk about, but I'll tell you the results because it's kind of interesting. So first, I want to discuss Langland's disjointness, which consists of a definition and an important theorem. Let's just say that data P and sigma, P1, sigma 1, and P2, and sigma 2 are related by associateness or associated. People just say associated in English. This is a certain equivalence relation. So this relation is a type of conjugacy, but it's a conjugacy involving not the P subgroups, these block up a triangular subgroups. It's a conjugacy involving the L subgroups. So there should be some element such that K conjugates the Levy factor of one of these fellas onto the other one, like that. And these sigmas, of course, are representations of L. In fact, they're representations of a factor of L. And what we'd like to say, let me see if we can get this right now, is that the representation pi 2, which is, sigma 2, which is a representation of L2, or if you like, a representation of M2, if this is equivalent to the representation you get by first conjugating with K, I guess, which sends you from L1 to L2. No, I want to go from L2 to L1, K inverse, and then applying sigma 1. And in this situation, it turns out that everything attached to P1 and sigma 1 is the same as everything attached to P2 and sigma 2. So here's the theorem of Langland's. If they are associate, then every representation of G which occurs from using parabolic induction from this data is equivalent to every representation which occurs from this data here. So take sigma 1 tends to some phi. Is equivalent. Induction using not P1 but P2, and not sigma 1 but sigma 2, and some corresponding phi 2. And what it means is that when you look at this direct sum, there's really no point in putting in a summand for both P1 and P2, because they're duplicate. If you drop the P2 summand from this sum, you'll still get an injection. And so we only have to sum over associate classes. The map exactly like the one I've written here. Oops. I do want to make one change. I want to sum now just over representatives. Associate classes. This map is injected. We're not done, or Langland's is not done. Because he also says what happens in the non-associate situation. In the non-associate situation, there's never any coincidence between these representations. So, if these are not associated, I guess. So I was using associated. Then no component of any one from representation coming from the first of any. So I take sigma 1, answer any phi 1, and now I induce up to G, and I get a unitary representation of G. And it may not be irreducible, but at least it's completely decomposable, and so it decomposes as a direct sum of irreducible representations. What I'm saying is that the irreducible representations you get that way have nothing to do with the ones coming from P2. No component is equivalent to any component of any one of these fellows. They're completely disjoint from one another in the strongest possible sense. And what this says, by a small C-star algebra calculation, what this says is something very interesting. Let's call this map something. We haven't used the star for a while. We know this map is injective, so the image of star is an isomorphic copy of the reduced C-star algebra of G. And what this fact says is you can commute the C0 direct sum with the image in the following sense. This is just the C0 direct sum over representatives as before. Of the image single factors. So if you want to know what the C-star algebra is, you just have to look one constituent at a time and understand what one of these fellows is. And remember that this thing here is just the functions from this topological space into the compact operators on the Hilbert space. That's what it looks like. So the C-star algebra of G is a direct sum of little parts, and each part is a subalgebra of such an easy C-star algebra as this. So it's not so bad. Yes?
What is the relation between phi 1 and phi 2?
Nothing. Phi 1 is a character of the A1 group coming from L1. So L1 is M1 times A1. And phi 2 is, phi 2 is similarly a character of the A2 group. And in this statement, you can let phi 1 be anything. And you can let phi 2 be anything. In this statement up here, you have to, given phi 1, you have to choose phi 2 appropriately. And it won't surprise you at all to learn that what you should do is conjugate. If you conjugate by k, you'll calculate right away that k conjugates A1, the group A1, into the group A2. And so we can compose, as we did here, with the conjugation operation to transport phi 1 and make it a representation of phi 2. So in the first statement, where we have to choose some phi 2, we make the obvious choice, and it's the good choice. And in the second statement, it doesn't matter what phi 2 is. There's never any connection between the representations associated to this fellow and the representations associated to this fellow. And we're nearly done to understand what the C-star algebra looks like. This is not... This is within the reach of techniques like the techniques that we were discussing earlier in the lecture, in the course. We were discussing this Hilbert module that I like so much, this C star of G mod n, which is due to Pierre Clar. We were discussing it, and if you study the Hilbert module C star of G mod n, then you can prove these results. These are within our reach, but sadly the time does not allow us to go there. The next statement is a little more complex. And as I understand it now, requires more sophistication. So the question is, what does one of these individual images look like? We know what one of these individual images look like. We know what they all look like. Then we'll know what this looks like, and therefore we'll know what the C-star actually looks. And for that purpose, it's very natural to study the following group. Namely, the group of elements in K which conjugate L into itself. It's natural in the light of Langland's results. And which have the property that they also conjugate sigma into itself up to equivalence like this. This is a certain group, a sort of normalizer group. Inside of it is K itself, or the part of K which lies inside of L, as that's a normal subgroup. That's these are the trivial elements which conjugate L into itself. And it's always the case that inner automorphisms preserve representations. So you want to divide by that trivial group. And when you do, you get a finite group. Not too hard to show. The name is a little unfortunate because despite calling it W, it's not necessarily a Weyl group. It's some finite group. So this group acts on A. So what I'm imagining is that we're given a parabolic, which is an M, A, N, and a sigma by automorphisms. Namely just conjugation. And hence on A hat. On the space A hat, the topological space that you see. And the final big result that we need is this one due to Harish-Chandra. And for this, I'll show you how this looks. It's rather beautiful. I'll show you how this looks for SL2R, where it's very elementary. But in general, this is quite a complicated result, I think, still. You can state it very easily in C-star algebra language, but at the moment I don't know how to prove it in simple C-star algebra language. So we have an action of W sigma on this C-star algebra. And what I want is the compatible action on the module. So this, remember, was a C-star module over C0A hat. And the actions on the module and on this space should be compatible. In a compatible way. And in a way which is compatible with the action of G, the G equivariant way. So when I say compatible, I mean compatible with both C star of G and with the action of W on A. And finally, the image is the answer to our question, wherever it was, yeah, the question up there. Turns out, well, there's a subtlety here, which is that the way in which W acts on this module is not completely determined by what I've written down. Nevertheless, the action of the induced action on the compact operators is determined, and the image of this map is exactly the W fixed part of the compact operators. So this W fixed part is independent on the choice, because there are choices of actions. They don't differ much from one another. But there are small choices you can potentially make. It doesn't matter how you make the small choices, you always get the same thing. So now you can put the whole thing together, all of these things. And reach what you might call almost a grand conclusion. This is almost the answer to the question, what is the tempered dual? It's almost the answer to the question, what is the C-star algebra of G? So there's a natural representation now on the C0 direct sum of over representatives of associate classes. Here I'll put the compact operators on this module ind of sigma. This notation has a defect that P is not mentioned explicitly, even though the construction, which uses parabolic induction, does use P. It's defensible because it turns out that different choices of P give rise to isomorphic modules. And I forgot to put in this. So what's going on is we have a family of infinite dimensional Hilbert space bundles over a family of vector spaces. That's what these in sigmas are. And on each of these infinite dimensional Hilbert space bundles over a finite dimensional vector space, a finite group is acting. On the base, vector space is acting basically through permutations of basis elements. But on the fibers, it's doing something mysterious. And we obtain such a formula as this. So we're getting pretty close, but not exactly, because we haven't totally nailed down how this group is acting in the fiber direction. I'm just saying an action exists, and it gives rise to such a statement as this. So it's almost the grand conclusion. Fortunately, the experts have gone one step further. So this is more or less, I should say, let's just take a pause briefly to look at what happens for SL2R, try and understand a little bit what's going on. So let me talk about that first. Then I'll get to the final grand conclusion. there's only one P of interest, which is this one. So L is the actual diagonal subgroup. This is supposed to be a product M times A, and M is not a very complicated group. It only has two elements, namely plus or minus the identity. As for A, it's isomorphic to a one-dimensional vector space. It's just the group of positive diagonal matrices, like that. So there are two sigmas. Well, first of all, I'll write that down. There are two sigmas. So these are discrete series. In this particular case, M, well, is a finite group. Every irreducible representation is a discrete series representation, and there are two of them. There's the trivial representation of M, and there's the non-trivial representation of M, and that's it. And in both cases, this group W is the two-element group. So this was a collection of elements of K which conjugate M into itself. So here's the definition. And not a lot going on here. Here's an element which conjugates the diagonal subgroup into itself. Just switches the two entries in L. And there you go. The induced conjugation action on M is trivial because this is plus or minus the identity matrix. This is actually the center of SL2. There's no action on M whatsoever, and therefore this clause here is, of course, trivial. This is a non-trivial condition, but the other condition is not trivial. All right, so there we go. And let's try and understand what this module is. Well, it's just the C0 functions from the line, which is A hat, with values in some copy of some infinite dimensional Hilbert space. And I'd like to write this in the following way. This Hilbert space is a representation of K, and it breaks up, which is SO2, and it breaks up as a representation of K into one-dimensional weight spaces. And the weights that occur are either this is the case where sigma is non-trivial, or this. In the case of the trivial representation. Right, and that's right. What about the action of W sigma, or the non-trivial element of W sigma? We know how it acts on the real line. It just acts on the real line by flipping the real line backwards and forwards. But how does it act on this Hilbert space? Well, it depends. There are two possibilities, and one possibility is this, just the identity on L2 in the even case. But the way it works in the odd case is the identity on L2 of, I don't write this as 2. I want to write down, I want to write the odd integers, I want to break up the odd integers into those which are positive and those which are negative. Maybe I'll write that as 2z plus 1 plus or minus the identity on L2 2z plus 1 minus. As it happens. That is to say, you can make these choices as guaranteed by Harish. And if you think about it, when you take this calculation and you work out what this C-star algebra is, here it is, this summand is, what you find is that the two summands, even though they both look like C0 functions, the compact operators in both cases are C0 functions from the line into the compact operators. In both cases, the group is a two-element group, and in both cases, the two-element group is acting on the line in the usual way. Despite all of those similarities, because of this small difference here, you get two different C-star algebras in these two cases. So the C-star algebras which come out of this are different from one another. In fact, they're so different that they're even different at the level of K-theory. K0 of this summand is either 0, this is what happens when sigma is the trivial representation, or Z, this is what happens when sigma is the non-trivial representation. Aha. So back to K-theory, these two summands behave rather differently. And now we can discuss, finally, after having looked at this example, what is basically the ultimate statement. It's always dangerous to say that, but it's some sort of conclusion. Final statement about the structure of C-star algebra. And I guess I wrote down here an explicit formula for these intertwiners in coordinates. There's another way for SL2 of obtaining these intertwiners, which is by an explicit formula for the intertwiner in its natural coordinates, And here remember these Hilbert modules look like, functions on G mod n. I don't think I'll go into, let me not say anything more, except to say that you can actually realize these intertwiners using the Fourier transform in the case of SL2, but let me not say any more than that. Okay, back to this business here. All of the things I've been talking about are within reach, in my opinion, of the theory of C-star algebras and geometry, are within reach of the techniques which I've been discussing. Everything that's written here, we can more or less understand, I can more or less understand as a poor functional analyst. But now comes some more detailed analysis, and I have no ambition to understand what's written down here, what will be written down here in terms of functional analysis. This seems to me to be genuinely more subtle and detailed. So this is the final work in classification of representations due to Knapp and Zuckerman. Actually, and many other people, but these are the two people who made the final steps, the crucial final steps. Let me put in Stein as well. Okay, and what I'm going to describe is a much more detailed analysis of this group here and the way it acts on this module. each of these groups can be decomposed into something into constituent parts, each of which is a little bit simpler. A certain normal subgroup, W sigma prime, and a certain group, R sigma, like this. And what's the story with these bits and pieces? Well, the good news is that at least W sigma prime has an actual definition, which is easy to understand. It's exactly the elements in W sigma with the property that the action of this element on this in particular induced representation. So in our analysis, we were considering families of parabolically induced representations which all differed by a character of A. Here I'm going to take the character of A to be the simplest possible thing, the trivial character. Now I have a single irreducible, not irreducible, a single unitary representation of G. And this K, according to Harishchandra, acts as intertwiners on this space. And this K may or may not act as a trivial intertwiner. And trivial in this case means multiplication by a scalar. The actual action of this element is not well defined because there are different ways of constructing intertwiners, as in Harishchandra's theorem. But whether or not it's a scalar is an invariant thing. Of course, scalars always intertwine in group actions, so these are boring. And as for R, it's actually just a product of group C mod 2. It's a very, very trivial group like we saw. Well, here is Z mod 2. And so this is not, again, I'm translating into C-star algebras, but it's rather beautiful what happens. If you're looking at the compact operators on the Hilbert module in sigma, and you're looking at the W fixed part, which you should be doing to understand the C-star algebra of G. This is not isomorphic to, but it's Morita equivalent to, isomorphic in this category of non-commutative topological spaces to some very, very elementary thing. Namely, you take A hat and you divide by the action of W prime. And now we have the continuous functions on a quotient of a vector space by a finite group, actually a Weil group. W prime acts as a Weil group, reflection group on A hat. And then you do a twisted tensor product construction, what the C-star algebraists would call a cross product. Other people just call a twisted tensor product. Because R normalizes W prime, it's a fact that this group acts by homeomorphisms of this space and therefore automorphisms of this C-star algebra, and this is the corresponding twisted tensor product of the continuous functions on this space with this finite group, or that is to say with the group ring of this finite group. That's it. So the grand conclusion is therefore, let's keep this here for a moment. Is that the C-star algebra of G is isomorphic, well, in this category we discussed of non-commutative topological spaces, the C0 direct sum of almost abelian C-star algebras, namely you take A hat and you divide by this W prime. twisted by some finite group, which is just a product of Z mod 2s. And putting all of this together and doing a final calculation here, the K-theory of the C-star algebra of G so in order to calculate the K-theory of this, you just have to calculate the K-theory of this. And it turns out that's not so bad. You can calculate what the K-theory of this is. And the answer is, well, it's a dichotomy. If W prime is a non-trivial group, the K-theory of this is always 0. But if W prime is a trivial group, the K-theory of this is always Z. This is under the assumptions with which we began the lecture. And so what you get here is exactly this statement. Let's just check in this example. Oh, good, it's still here. Here's a description of the action of W sigma, and we can compare this description with this definition of W prime to figure out what these various bits and pieces are going to be in the particular case of SL2. So the action on the basic representation, base representation should be a scalar. So that's going to be the case here, but it's certainly not going to be the case here. So what we find is that, let's just take here the case where sigma is trivial. In the trivial case, it's the R group which is trivial, and the W prime group is equal to all of W. And in the other case, it's the R group, which is equal to everything. It's the W prime group, which is trivial. And to so this is not by any means simple business, in my opinion. I do not know how to prove this theorem. I know how to find the statement, but I do not know how to prove it. There's a lot of careful examination of more combinatorics involved in proving this thing. And yet the answer has to be consistent with something which is incredibly robust, which is the K-theory, because exactly how these W primes and R's work out has a meaning at the level of K-theory. You can see it at the level of K-theory. And this K-theoretic statement, I mean the Connes-Kasparov conjecture, is something which is incredibly robust. There's a version of this statement for every Lie group whatsoever in the whole world. In fact, there's a version, conjecturally a version for every group in the whole world. So on the one hand, we have this incredibly robust statement. On the other hand, we have all of these very subtle details in representation theory, and how exactly they relate with one another, it's very hard to understand. So let's just let me draw one more picture. I'm not going to tax myself this time. Let's just continue to study SL2R. So what I'm drawing here are the Harish-Chandra parameters. Which turn out to be integers in the case of SL2. And nearly all of them are non-singular. So somewhere here is 0, and all of the rest are non-singular. Like this. But right in the middle is a singular, which is 0 here. When you look at the C-star algebra of SL2, there are, according to this description, there are a variety of summands into which it decomposes. There are 2 summands associated to principal series, depending on whether sigma is a trivial character of a 2-element group or the non-trivial character of the two-element group. And the only other possibility for things inside of the C-star algebra of G are summands of the compact operators corresponding to discrete series. So the K-theory consists of one generator for each discrete series representation, and then one generator for the non-trivial sigma, and then 0 generators in this case here. And that's exactly what happens here. So these are the non-singular parameters, each of which maps under the Connes-Kasparov map to the discrete series with the same non-singular parameter. And this guy here is singular. Oops. And it maps to this fellow here. This particular Z here. In the case of the discrete series, we have a complete way of understanding what is going on. In the case of the discrete series, we understand, because we have a lot of experience with them, we understand Dirac operators and the index of Dirac operators. We understand how to extract the classification of the discrete series from the Connes-Kasparov conjecture, and we understand how to use the classification of the discrete series to prove that part of the Connes-Kasparov conjecture, so to speak, the red part of the Connes-Kasparov conjecture. And so it's fair to say that the problem of classifying the discrete series and the problem of verifying the Connes-Kasparov conjecture are exactly the same. They're equal in difficulty. You can easily do one using the other and vice versa. But then there are these other generators. There's the singular part of the Connes-Kasparov conjecture. And it's a little paradoxical and confusing that this is much harder, or it seems to be much harder, than the discrete series part. People think of the discrete series as the most fundamental part of the representation theory of G, because once you have the discrete series, you can describe everything else by parabolic induction. But when it comes to the fine structure here, or if you like, verifying the Connes-Kasparov conjecture for the non-discrete series, for the singular part, this remains a very complicated project. There should be some way in which the combined Connes-Kasparov conjectures for the discrete series parts of G and all of its Levy subgroups should imply the Connes-Kasparov conjecture, the singular part of the Connes-Kasparov conjecture for G. But we don't know how to do that yet. So at this point, the story ends and the problems begin to prove in a conceptual way exactly what goes on for this singular part of the map. In any given example, we can calculate, but if we want to understand conceptually some of these very complicated statements using K-theory, this is a project for the future, for next time. So thank you very much.
Thank you very much for great and impressive lecture series. So any question moment? So maybe this is the last time for you to ask.
Last chance.
Virtual flower, send over.
Well, thank you again for your patience. It is great to talk in front of the person who learned the most in these weeks probably was me. So thank you for teaching me so many things, making me learn so many things about representation theory.